Okay, so I want to make a video about forces. There are four main forces well, there's several forces that we have in our AP Mechanics class, but there are only a few that we can calculate using different equations. So I can talk about things like a tension force. I can talk about a push force, pull force, an external force, all kinds of forces that we have. But there are a few of them that we have an actual equation for that we can use to calculate. Any of these tension forces, push forces, pull forces, etc., we'd have to measure them directly using something like a force probe or a Newton meter, or we'd have to use something around, say, Newton's second law or Newton's first law to relate one of these tension forces or push forces to a known force that we can calculate, and then we can calculate that force. So without using Newton's laws, we can't really figure out what a tension force is or push force or any of these external forces, just because we just don't have an equation for it. So the first thing we should talk about are the forces that are really important for us in this class that we can actually calculate. And those forces are gravity, spring force, or the elastic force. I prefer the term spring, but either one is, or I will use the term spring, but either one is correct. There's also a friction force, and there's two kinds of friction, well, two flavors. There's the sticky kind, which is when things stick to the ground, and that would be our static friction. And then there's our slidey kind of friction, which happens when two surfaces are in contact and they are sliding against one another, and we call that kinetic friction. So with our four forces here that we can actually calculate, we should probably do a little bit of work on them, try to figure something out about them, and maybe start putting them together with Newton's laws in a future video. First one that we'll talk about is gravity. This is the one that we have the most experience with for sure. Our force of gravity, that's going to be equal to an object's mass times this gravitational acceleration vector g. Now notice I do have the bars over these equations, so this is a vector equation, and what we see is something with a magnitude and a direction. So when I talk about my force of gravity, I should know that it always points towards the center of the Earth. About better? Always points towards the center of the Earth. And for us, near the surface of the Earth, where we are, approximately a horizontal flat surface, that means we will point down. So near the surface of the Earth, F sub g will point down. And I'm saying it points down, not in the negative y direction. The reason why I'm saying that is because we can certainly say down is positive y if we wanted to. However, it's not often really beneficial to do that, and it kind of goes against our intuition. So a lot of times we'll just say down is negative, but still, it points down all the time. So if I think about my force of gravity, I know it's going to pull on something, it's going to cause it to fall. Even if I start with zero accelerate or zero velocity, it will cause some sort of acceleration that we say is g, which is equal to 10 meters per second squared pointed downwards. If I want to draw a vector for force of gravity, it would just be like this. There we go, force of gravity vector. This has a direction and a magnitude, so the magnitude is however long this vector is, and the direction is, well, down. But the force of gravity can't really be calculated as a vector equation, or maybe it doesn't really make sense to us. So maybe we should think about the scalar version of this. So if I think about the scalar version, I can just write f sub g with no bar. So again, there's no bar up there, just an f sub g. And that is equal to m times g. And again, no bar above the g now. So now we don't have any sort of direction to this. And so these are positive scalar values. F sub g is the scalar value of the force of gravity, or what we call the magnitude of the force of gravity. Mass is always a scalar, and then g here is going to be a positive 10 meters per second squared. If we wanted to worry about whether it's pointed down and that's negative, or up and it's positive, or maybe up's negative and down's positive, However we want to assess that, we'll deal with that in the Newton's second law stuff when we start drawing free body diagrams. But for now, let's just keep it simple and say that the force of gravity is equal to mass times the gravitational acceleration constant, g. So again, we know that g is going to be a positive 10 meters per second squared. I think we talked about this earlier, that a scalar is always positive. We also have our mass, which is something unknown to us, or maybe we'll have to calculate it, or it'll be given to us and we'll be asked to calculate the force of gravity. But then we also have this force of gravity quantity here. And this will be a unit, or this will be something that has units of newtons. And you can kind of think about it, well, what does mass have units of? Well, in our physics system that we use for mechanics, we use the MKS system, stands for meters, kilograms, and seconds. The MKS system, we like to use kilograms. So when we talk about mass, we use kilograms. There's other systems that we could use. There's the CGS system, which stands for something like centimeters, grams, and seconds. Something that they use in like solid state physics or E&M applications, but for sure solid state physics. Anything that uses small molecular quantities. But again, we are the meters, kilograms, and seconds units, and so we will think of our mass as being in kilograms. We also know g has units, and those units are meters per second squared. So when we put all these together, we get we get a kilogram times a meter over a second squared, and that is something we define to be the Newton. Right, so the Newton obviously is named after Sir Herschel Newton, the third Duke of Earl. It's actually named after Isaac Newton, the famous physicist. He came up with this whole idea way back when, and this has been a really important part of our analysis and our beginnings to understand what physics is. So force of gravity can be calculated as F sub g is equal to m times g. So moving on, let's do an example or two. If I have a force of gravity acting on an object, and I want to know how much force gravity or the Earth's gravitational field is exerting on this object, well, I could figure out what what the mass is using a balance or something like that. And let's say that we got our mass is equal to 40 kilograms. So our force of gravity we can then calculate as being 40 kilograms times 10 meters per second squared. And the result we get is 400 kilograms times meters per second squared, or 400 newtons. So our force of gravity magnitude would be 400 newtons. At this point, we'd have to determine, if we were going on to do a dynamics problem, a full Newton's second law or third law problem, we have to determine what direction it is, and then we say maybe down is our negative y direction, and so what we would say is F vector is equal to negative 400 newtons in the y direction. Again, this is a y with a little triangle thing, a little 2/3 of a triangle thing on top of it. We call that a hat, and it represents the y unit vector. And it has the y unit vector has a magnitude of 1 and points in the y direction. There's also the x hat vector, which has a magnitude of 1 and points in the x direction. So this x hat, y hat stuff gives us our directional capability, and this negative sign tells us it's in the negative y direction. But the 400 newtons, this piece right here, this is the magnitude of our force. And this, combined with our negative sign, is our direction of our force. Okay, let's do maybe one more, a little bit different. Let's say that we have a force of gravity and we measured it, and we got around, let's say 35 newtons is what we measured. We hung this on a force probe, and the force probe read 35 newtons at a steady rate, so it's an unchanging 35 newtons. And we know that the force of gravity is equal to mass times g. We also always know what g is. That's a constant. So we can just calculate without any additional information what our mass is. So I'm going to go ahead and start over just writing out my force of gravity equation just to be complete. I'm going to divide through by my gravitational value, g. My g's will cancel, and I'm left with just our mass on this side, and I get mass is equal to the force of gravity divided by g. We measured that force of gravity again. We got 35 newtons from our force probe. We divide that by 10 meters per second squared, And what I get then is 3.5 newtons per meter per second squared. Does this make sense? Well, what is that unit really? Let's think about it. Let's do some what we call dimensional analysis. Our newton, we said, is a kilogram times a meter over a second squared. We are dividing that by a meter per second squared. So this thing, my right side of my equal sign, is going to be divided by a meter per second squared. Meters cancel, second squared cancels. I am left with kilograms, which is units of mass. We are indeed calculating mass, and so we are happy. And we call this something like 3.5 kilograms. So basically, when we do force type of problems, they're going to be what I call quick calculation problems. You'll either have to do like some really, really easy, really fast division or multiplication to do some algebra to move stuff around a little bit, but that's about as hard as it's going to get. From there, you just have to plug some numbers into your calculator and you'll be able to calculate a force or a mass or maybe even verify the gravitational constant like we'll do in the lab soon. Next force that we should talk about is called the it's called the spring force or the elastic force. I always call it the spring force. I'm going to write it as F sub spring SPR. This force of spring vector is equal to minus K times delta X vector. So delta X is the vector, K is not a vector. And maybe we should talk a little bit about what these things mean. So our force, the spring force, obviously that's going to be the force. It's going to point in some direction. It'll have units of newtons and maybe some length of the vector, which we call our magnitude. This K thing, this is new to us in a lot of ways, and so we should probably talk about it for a moment. This is what we call the spring constant. You can also call it the force constant. Or if you're really fancy and you can spare the time, you could call it the spring force constant. There's other things you can call it, the spring coefficient, the force coefficient, the coefficient of force, something like that, but it all means the same thing. It's basically telling you if I stretch this spring some distance in meters, it will exert a force back on me. And this equation here, this whole equation, is given a special name called Hooke's law. Hooke's law is what allows us to do this calculation and figure out whether our spring is going to exert some force when stretched a distance. We can measure what K is. Sometimes K is given to us by maybe the manufacturer's data sheet, or maybe we just know it off the top of our head because we've had some experience with this particular type of spring or elastic situation. But the point of these are, if we have a spring that obeys Hooke's law, it will be linear in stretch distance versus force. What I mean by that is if I look at a plot of a force versus spring distance, so here's my delta x on my horizontal axis and my force of spring is on my vertical axis. If I were to start by not stretching at all to the natural length here, I would have zero force. If I stretch it some distance, we'll call it x sub 1, I would get some force F sub 1. If I stretched it further, maybe double that distance to x sub 2, I should get some value F sub 2, which should be roughly double the F sub 1 value. And what we get if we were to plot a bunch of stretch distances versus force, force versus stretch distance, I should say, what I'd get is this line that would be a y is equal to mx plus b type of line. And this m is going to be a slope of this line, and it looks kind of like our force equation, right? So if we think about this could be like m is equal to negative k, x is our delta x, and b, well, what's b? We pass through 0, 0, and b is our y-intercept, so b would have to be 0. And that would make sense because we shouldn't have force if we're not stretching the spring. So our y equals mx plus b type of line ends up becoming a force is equal to minus ax type of line. And this was only true for certain springs. Not all elastic things like rubber bands don't obey Hooke's law. They have a non-linear component to them. I think it's quadratic or tertiary or something. But these, most springs that we encounter in our day-to-day life are roughly Hookean, as we'd say. So they do obey Hooke's law. And we can certainly approximate them, for very even non-Hooke laws type of springs, non-linear springs. Even these can be approximated for small stretch distances. or small distances, differences in stretch distances. So Hooke's law is a really, really important thing because it lets us do a lot of cool stuff. In physics, we absolutely love springs. They're our most favorite thing ever, and especially in our early mechanics world. Springs are really cool because they do a lot of stuff. In addition to just being a spring that does spring stuff, it also allows us to calculate mass, allows us to measure G, we can measure K value of springs, all kinds of fun things that we can do with springs. But also when we stretch a spring and we start plucking on it, it does this thing called a harmonic oscillation, and we'll talk about those next semester. So if we wanted to calculate our spring law, ultimately we could just take our force of spring as a scalar. Again, I don't have a bar over this quantity, so it's a scalar quantity. It's going to be positive, and it has no direction, but it will have units of Newton still. So our force of our spring is equal to minus K times this X thing. Oh, pop-up happened. So minus K times X. So K, again, the spring constant, has units of newtons per meter. X is the distance that we stretched. So if I have a spring, let's say it's natural length, and measure that with a meter stick or tape measure or something, I would get this natural length L sub 0, or L naught. L naught is what we call the natural length of the spring. Natural length of the spring. And L naught is something we really need to know to be able to work with this spring. L naught is kind of an important quantity because that's what gives us our zero force. If this spring is stretched to the distance L naught, then we'd have something like minus K times delta X. But delta X is our final minus our initial, so X final minus X initial. What is X initial? Well, that would be our unstretched length. So we could say K times X final minus L naught. And maybe we could call X final something else. What if we called it, what if we called X final L, the new length, stretched length, the length that we have stretched this spring to? We get this equation that says K is equal to L minus L sub 0, or L minus L naught. And our spring force can be expressed, our spring force equation can be expressed in two different ways. We can have a minus K times L, length of stretch, minus L sub 0, our natural length, or we could have minus K times delta X, which is our distance that we stretch the spring. If we don't know what delta X is, if it's not given to us, we'll need to know what the natural length of the spring was. We'll also need to know what the final distance that we stretched it was. So if I measure my spring here in L naught, for my initial measurement of L naught, let's say that L naught was equal to 10 centimeters. And then I stretched it and I measured the spring again, and I got L is equal to 25 centimeters. That means that I would have to plug in 25 minus 10 and get a positive 15, and that would be my delta X value. I could also be told in a problem statement maybe that my spring was stretched by 15 centimeters. Either one will give you the correct answer, but you just need to be sure about what they are giving you. Is it a distance, natural length of the spring plus a stretched length of the spring, or is it the actual distance that the spring was stretched for? All right, let's do an example or two about the spring force stuff and using Hooke's law. Let's say that I have a spring, and the spring coefficient, or the coefficient of force, or the spring force coefficient, or the whatever you want to call it, was 15 newtons per meter. What this thing is telling me is that if I stretch it a distance of 1 meter, I will get 15 newtons of force out of it. Also, it's telling me if I stretch it 2 meters, I will get 30 newtons of force out of it. 3 meters, I'll get 45 newtons. So K value is really what characterizes the spring's ability to pull itself back together. The K value determines how stiff a spring is. So a very, very stiff spring, like something you see in your car shock absorber, that's going to be a very high K value. But something like a slinky is going to have a very low K value. It's very easy to stretch a slinky, not so much so to grab a shock absorbing spring from a car and push it or compress it or whatever. So K values are usually given to us, or we have to calculate them. They can be given to us by, like I said, a manufacturer's data sheet. It can be given to us by previous experiments, something like that, or we can directly calculate them using a Newton's law thing. But for today, again, we're just doing our quick calculation stuff on spring forces. So spring force is k minus k delta x. Our k value is given to us, and let's say that we then stretch this spring a distance of 17 centimeters. Why not? My spring force equation from Hooke's law says the spring force is equal to minus k times delta x. And again, this is kind of a weird thing. I like to leave the negative sign in there because it makes sense. But you don't really need to. You can calculate the spring force, and then you just have to, correct it with a negative sign to make sure it points in the right direction in your free body diagram. But for today, we'll just leave the negative sign on there, just to be complete. So negative k, that's going to be negative 15 newtons per meter. And then we multiply that by our delta x value of 17 centimeters. However, the units of k are newtons per meter, not newtons per centimeter. So we can't just use 17. We have to be careful about our units. We'd have to convert this to meters. So that would be 0.17 meters. And we could use 0.17 meters because it now cancels out meters in the bottom of our k constant. If I plug this into a calculator, I should get something around about 2.55. And our units for meters have canceled, leaving us with just our newtons. We have that negative sign out front, which tells us it's going in the opposite direction that we are pulling it. And that would be our answer. Okay, let's do another one. Let's say that we decided to test out this spring. We got some unknown k value spring. We have no idea what this thing is. We pulled it out of our stock room in the back, and as we know, things that sit in the stock room for a long time, they don't last long. So we don't, or information about them doesn't stay around long. So we need to figure out what this k value is for our spring. You might say, there's plenty of ways we could do it, but the simplest one is to probably grab a force meter or something like that, a Newton meter or force probe, and pull on the spring a certain distance, measure your distance, and then from there calculate your k value. You could also, probably one of the most classic ways of doing it is measure several different masses, hang them from a spring, and then plot the data and figure out what the slope of that line is, which we already did that in class. Okay, so our k value is not unknown, and we can calculate it by taking, say, a mass or something, but here we'll just say we have a force probe, so we pulled on it a distance, and we got this force out of our force probe that says the force was going to 40, let's say 20 newtons. Force of the spring was 20 newtons, and that was because we stretched it a distance of delta x is equal to 1.5 centimeters. This might be a pretty stiff spring. 1.5 centimeters, I have to convert that to meters, so that'd be 0.015 meters, also 15 millimeters. But we want meters again, so we'll use that. And then I'd set up my equation that says our spring force is equal to minus k to x. Here, I'm just going to actually toss out that negative sign because it's going to make things a little simpler. I'll explain why in a future video I'm tossing out that negative sign, because k values are always positive. K values are never negative. So if I stretch a spring, I'm not going to get a positive force back. And that would happen if I had a negative k value. So I have a negative k, and that would give me a positive k delta x is equal to my force of my spring. So that tells me if I stretch my spring, that my spring is going to push outwards, and that's not something that happens. So we'll just use our simple case of F spring is equal to k times delta x. We would divide through both sides by that delta x value. And that leaves us one side, the right side of our, oh, wow, that was weird. That leaves us with one side of our equation with just a k, and the other side of the equation as the spring force, which we measured using a force probe, divided by delta x, which we would have also measured using something like a meter stick. So our spring force is 20 newtons. Delta x is 0.015 meters. And then all I need to do is plug that into my calculator. I get an answer somewhere around 1333.33, and it just keeps repeating. Again, this is an AP physics class, so when you take the AP exam, they're going to want you to kind of be reasonable about the number of sig figs. I have like 2 sig figs down here, maybe 1 up here, rough guessing. So I'm going to just call this 1300. And my units are newtons per meter. You might say, hey, wait a minute, aren't there meters in that Newton thing? And yes, you'd be correct. A Newton, again, is a kilogram times a meter over a second squared. So if I divide this whole thing by meters, my meters will cancel, and what I'm left with is a Newton per meter. That's a kilogram per second squared. So I could say it's also 1,300 kilograms per second squared. One of these is related to frequency. One of these is related to a stretch distance. However, I would really prefer that when calculating a K value, you give me a Newton per meter. I think it's a more standard thing, and for this portion of the class, it makes more physical sense to use a Newton per meter because we are talking about forces in this unit. So when you do give me a solution, make sure that you give it to me as newtons per meter, and I will be happy with that. However, I'm not going to limit you. You can certainly use kilograms per second squared. I prefer that you use newtons per. Okay, so that's how we would calculate like a K value. We would calculate the force of the spring force by using K delta X. Maybe let's do one more where we're not given delta X. We'll try something where we measure natural length of our spring. Then we will take that and measure the stretch length of our spring as well. So let's say that I measure my spring that's unstretched and I get L sub 0 is equal to 30 centimeters. 30 centimeters is 0.30 meters. That's what we want, meters, not centimeters. We also know, maybe we have our manufacturer's data sheet for this particular spring, that our K value is equal to 25 newtons per meter. So if I stretch this thing and I measure it and I get a final stretch value of L is equal to 0.50 meters, so about half a meter, well, half a meter exactly, then I could sit here and apply my spring force equation. So it says F spring is equal to minus K times delta X. But delta X, we don't know that. We'd have to find out what delta X is, and we could do that using delta X is equal to stretch final minus stretch initial. Just like we talked about in the kinematics section, delta X means a change in something, and so it always means final minus initial. So when we see delta X in our F is equal to minus K delta X, that means it's a change in position. So X is equal, or delta X is equal to L minus L naught. I can plug that in for delta X. I get minus K times L minus L naught is equal to my spring force. From here, I can just plug in some numbers. I know I have 25 newtons per meter as my K value. I have a negative sign out front, and I have L is equal to 0.5 meters. And we subtract from that 0.0 meters, 30 centimeters. When I do the subtraction, I should get around 0.2 meters, and I'll multiply that by 25. When I do that, I would get the answer of 5. And my meters cancel, top and bottom. I'm left with newtons, and we get 5 newtons and a negative sign. Why did we get a negative sign even though I stretched it out and my delta X is positive? Well, that's because if I stretch this spring out, I would expect to have to exert a force of like a pull force on it to do that. But through Newton's third law, which we will talk about in another video, I will have a spring force exerted back on me as long as I am not changing my changing my velocity. So if I stretch out to some final distance, I hold it there where it has 0 velocity and it stays with 0 velocity, no acceleration, then this spring force will be equal to the pull force. And that should tell me that my pull force is going to be in the positive direction, but my spring force, well, sure enough, it's in the negative direction. Of course, that all depends on what we decide is the positive direction. If I were to say that to the right is the negative X direction, that would flip the sign on my delta X thing. And then my delta X would be negative 0.2, I would take that negative out front, those would multiply together, cancel each other out, and we would get a positive spring force pointed to the left and a negative pull force pointed towards the right, which we're saying is our new negative x direction. Okay, so that's Hooke's law and the force of gravity. I think we're getting kind of long in this video, so I'll go ahead and stop it here, but I will post another video on our two friction forces that we'll deal with. So keep an eye out for that, and we will see you later.